Hello everyone and welcome to week 3 of Math 2, working with some exponential and logarithmic functions. We're going to start with something pretty easy, that is just graphing with the graphing calculator. So if you have an exponential function, like for example number 1, y is equal to 4 to the x, which literally means take 4 times 4 times 4 times 4 times 4, which can get very big. Let's see what the graph looks like. So just go over to the y equals, and let me clear out this old problem, and then just have 4 raised to the x power. And of course, I always like to start with the zoom standard, so zoom number 6. And you'll see that the graph is actually very small right here, because that's when you have a negative exponent. When you have a negative exponent, that would actually make this 1 over 4, which gets very small. And then the function starts to grow right here. If you plug in x equals 0, well, 4 to the 0 equals 1, so the calculator should tell me if I plug in 0, it equals 1. So basically, if I have a y value of 1 right here, on this side, the function grows very rapidly, and on this side, it gets very small. Never actually quite gets to 0, but right there, it's getting very small. Okay, now what if it was a negative? Number 2, how about if it's y equals negative 4 to the x? What's that going to do to the graph? So we can just go y equals, and I could actually just put second, insert a negative in the front, and then how does that change the graph? So instead of going up on the right side, it goes down. So the negative basically inverts it. This part right here was above the x-axis, so if it gets flipped, so basically it just took this and flipped it down here, as you can see right there. So that means that this part is actually just below the x-axis. So whatever this little gap is above, it's now going to be below. So it's going to go like this, and then it's going to go down rapidly. And what about this point? Well, if this was positive 1 and you flip it down here, that should be negative 1. So if I plug in x equals 0, trace, and plug in a 0, it says y equals negative 1. So this is a negative 1. And then what if you put the negative in a different place? Y equals 4 to the negative x. So what about that? So let me go over to the y equals, and let me delete. You know what, it'd be easier to just clear the whole thing out and start fresh. 4 raised to a negative x. And what does that do to the graph? Well, it took the calculator a little bit to figure it out, but it finally did. So now it's basically switched. If you look at the original, so this is the original with 4 raised to the positive x, and basically it switched across the y-axis. So this got flipped over to here, this gets flipped over to there. And again, it's going to hit the y-axis at 1, and then it goes like this. So this, as it's going up and up, is called exponential growth. Oops, I forgot my W. Exponential growth. And then this is called exponential decay. So when it's getting smaller and smaller and smaller, then that's referred to as decay. Okay, next up, now that we've done graphing, solving some exponential functions. So there's this rule that says if you have something raised to a power, and then you have the same base raised to a different power, then since the b's are the same, that means the x has to equal the y. So this implies or leads to the fact that x has to equal y. So that's what we're going to use for the next 3 examples. So this must be example number 4. And what if it was 10 raised to the 9 minus 2x equals 10 raised to the 3x plus 1? Well, the bases are the same, so that means the exponents have to be the same. So the exponent 9 minus 2x on the left side has to equal the exponent 3 plus 1 on the right side. And then I can collect the x's on one side, so I'm going to add 2x to each side. And I'm going to take the 1 and put it over on the other side. So also subtract 1 and subtract 1. So these are going to cancel and these are going to cancel. So that means on the right side we're just left with 5x. And 9 minus 1 is 8. So that means that if you divide both sides by 5, x is equal to 8 over 5. Then for the next example, so for example number 5, so what if it was 2 is raised to an x plus 1, and then 4 is raised to negative x plus 2. And then you say, but wait, Mr. Perkins, the bases are not the same. And I say, yes, you're right. Our job is to get them to be the same. And I know that 4 is 2 squared. So I can rewrite the 4 as 2 squared. And then that's still raised to the negative x plus 1. And then just recopy the left side because it already had the base of 2. And then before I can set the exponents equal to each other, I should simplify this one so that it just looks like 2 raised to something. And then remember, when you have an exponent raised to another exponent, you multiply these two. So on the right side, it's really the base of 2, and then it's 2 times negative x plus 1. And now that the bases are the same, we don't need them anymore. So we can just say that on the left side, x plus 1 equals on the right side, and then this, I'm going to go ahead and multiply it out. So there's going to be negative 2x when you multiply these two, and then plus 2. Negative 2x and plus a 2. And by the way, when you're dealing with exponential functions, these exponents could be any number. Positives, negatives, fractions, decimals, anything. So if we get a negative answer, that's perfectly fine. All right, I'm going to collect the x's on the left side, so I'm going to add 2x to both sides and subtract 1 from both sides. And then these are going to cancel and these are going to cancel, so we end up with 3x equals, this is going to be a 1. And then just divide both sides by 3, and x equals 1/3. And then I do want to do one more like that, because there's also the possibility, this will be example number 6, that it's something like this. 1 over 8 is raised to a negative 2x plus 3. And then it equals 16 to the x minus 2. So the reason I wanted to do this one is, what if the base is actually in the denominator? So this 16 is not in a fraction, so this 8 right here, I don't want it to be in a fraction. So I can take the 8 and move it to the top as long as I change its exponent to be a negative. So if I put 8 to the negative 1, that's the same thing as the 1 over 8. And then I do need to still attach the exponent negative 2x plus 3. Okay, so in here I can multiply these two, which is going to make this a positive 2x plus 3. So distributing the negative makes it positive 2x. I think I just said plus 3. I meant to say positive 2x minus 3. And this one, its exponent is x minus 2. And why am I leaving blanks? Because I need the bases to be the same. So for an 8, so I've already taken care of the exponent, now I'm just talking about the 8 itself. Well, 8 is actually equal to 2 cubed. And 16 is actually equal to 2 to the 4th. So I'm going to replace this 8 with 2 cubed, and I'm going to replace this 16 with 2 to the 4th. Now we have the bases the same. So these exponents need to be multiplied, and I'm going to save one step and go ahead and do that right now. So that's going to be 6x minus 9. So 6x minus 9. And on the right side, this is going to be 4x minus 8. 4x minus 8. And then get the x's on one side. I'm going to subtract 4x from both sides. And then I'll move the 9 to the right side, or in other words, add 9. And then we get cancel, 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 cancel. This on the left side is going to be 2x. And on the right side, it's going to be 9 minus 8, so that's a 1. And the last step, divide both sides by 2, so x is equal to a half. Then there's another type of problem, and this is actually even easier. And this one comes from, in about 2 weeks, we're going to be taking the derivative, which is one of the most important ideas in calculus. And after we take the derivative, we'll get something like x times e to the x plus 5 times e to the x equals 0. And then we need to solve for x. We'll notice that there's an e to the x here and here, so we could factor out e to the x. And then what's left would be x plus 5. Okay, we've done the hard part. Now, when you have it factored and set equal to 0, you can separate it and say it's possible that the first factor equals 0, and it's possible that the second factor equals 0. And then if you look at the very first example that I started with, so this was 4 to the x. If it's e to the x, well, that's basically the same graph. The shape is the same. And notice right here, it gets closer and closer to 0, but never equals 0. So that also happens with this e to the x function, that it would look like this. And I can even use my red pen to look fancy. So it would get closer and closer and closer to 0, but it never equals 0. So that means that this one has no solution. Then I'd like to abbreviate that with just no solution. And then for this one, just subtract 5 from both sides, and our only answer is -5. And exponents can be negative, so the negative is not a problem. X equals -5 is the answer. And next up, what if it was just one step more? So for example, number 8, and again, this would come from, we take the derivative and we get something like -7x e to the x plus x squared e to the x equals 0. Since this has x squared, we're going to have two solutions. And we start off the same. Factor out e to the x. And also this has an x and this has an x, so it could also factor out an x. And then if this got factored out and the e got factored out, all that's left is a -7. And for this one, the e to the x got factored out and one of these x's is gone, so all that's left is plus a single x. And then set it equal to 0. Now we have 3 factors, so if you set each factor equal to 0, then it looks like this. The e function never equals 0, so that's where you can just say no solution for that one. X equals 0, that one's already done. And exponents can equal 0, negatives, positives, they can equal whatever they want. So in this case, 0 is fine. And then for this one, all I need to do is add 7 to both sides, so the other answer is x equals 7. Okay, now on to solving log equations. So when you have a logarithm, which is just abbreviated log, then there could be a number down here, which is the base. And then suppose that inside the parentheses there's y, and that equals x. So this is called the logarithmic form or the log form. And then I'm going to change it to exponential form. So in the homework, they will refer to the log form and the exponential form. So this is the log form. And what it means is the b is the base. And I actually remember it visually like this. I just draw an arrow. And that means that on the right side, it's got b raised to an x. And that little operation right there gets rid of the logarithm and it just leaves the y. And then that's the exponential form. So then for example number 9, if it was something like what's log base 2, in the parentheses there's an x, and then the 3 is on the other side. So this is saying that 2 is the base and you raise it to a 3. So on the right side there's a 2 raised to a 3. And that operation right there gets rid of the logarithm, so the only thing left is x. And then 2 cubed is 8, so the answer is 8. And for number 10, how about if it was log with a base of x, inside the parentheses is a 9, and then on the other side is a 2. So this is a great time to use the red pen and make the little arrow saying that x is going to get raised to the 2. So on the right side, it's going to have x raised to a 2, or in other words, x squared. That gets rid of the logarithm, then it equals a 9. And in order to solve for x, we need to get rid of this square, so just take the square root of both sides. Usually when you take the square root, you're supposed to put plus minus and get 2 answers, but with a logarithm, this number cannot be negative and this number cannot be negative. So this is the base, it cannot be negative, so I don't have to do the plus minus, I only need the positive 3 as the answer. And then let's just do one more with logarithms, like number, actually I'm going to do 2 more. Number 11, if it was 3 log base 5 x equals -9. In these parentheses right here, if it's only a single number or a single variable, you actually don't have to put the parentheses. So I could put the parentheses, or since it's just an x, I don't have to. So with all of these other ones, I did the red arrow first, but with this one, I first need to get rid of this 3. So if there's anything in front of the logarithm, you need to get rid of that. Since this right now it means multiply, then divide both sides by 3. So we're going to have log base 5 of x equals, and over here is a -3. So with the logarithm itself cannot have a negative right here, cannot have a negative right here. But this is actually an exponent. This side can be negative. Sometimes it is, sometimes it isn't. But this one is never negative, and this one is never negative. Now use the magic red pen and put the arrow like that, which means that on the right side, I have 5 to the -3. And then let's say that you're asked for a decimal answer. So then just get a calculator and go to the home screen and then say, what is 5 raised to a -3? And then as a decimal, that would be 0.008. If I go to math and say change it to a fraction, it will also give you the fraction in case you want that answer, or in case on the homework they're asking for a fraction answer. So you can just convert that to a fraction, and it's 1/125. Okay, then there's one more from logarithms that I want to do, and this would be number 12. And that is, what if it's log with a base of b, x, and then plus log with a base of b, x minus 2. And then it equals log with a base of b, 8. So basically with the previous examples, it was just like this. One logarithm and then equals something. What if it's plus? Well, the rule with logarithms, when you have a log base b plus a log base b, when you're adding the logarithms, you can change that into just one single logarithm as long as you multiply the arguments. So you multiply the x with the x minus 2. And just like in the beginning when I said if the bases are the same, then the exponents have to be the same. Or the other way to look at it is, since this is log base b and this is log base b, they're going to cancel each other out. So all we're left with is this, and I'm going to go ahead and multiply that out. So that's going to be x times x, or x squared, minus 2x equals an 8. And then I need to put everything on one side, so subtract 8 from both sides. And then either use the quadratic formula, which works all the time, or factor it. Well, with an 8, that equals 2 times 4. And I know that if I subtract a 2 and a 4, it will give me a 2. And this is a 2, so I think this one could be factored. If not, I can always do the quadratic formula because that will always work. But let me try factoring, because when it does work, it's faster. So for x squared, I need x times x. For 8, I need 4 times 2. And in order to get a -8, one of these has to be positive and one of these has to be negative. Since this result is negative, I'm going to choose the bigger number to be negative and the smaller number to be positive. And then if you look at the middle term, this is -4x, this is positive 2x, and -4 plus 2 is -2, so it actually worked. Then set this one equal to 0 and set this one equal to 0. So with this one, we just need to add 4 to both sides, so get the answer x equals 4. And for this one, subtract 2 from both sides, so x equals a -2. Now if you go back to the problem, with logarithms, this cannot be negative and this cannot be negative. Well, one of the answers we got was x equals a negative. That one is not actually a solution. So only the positive one is the solution. All right. A couple more, and then we get to do some fun word problems. So with number 13, suppose it's e to the 2x equals a 4. So with the e function, if you look on the calculator, the e function is right here in blue, and right next to it is the natural log function. The reason they're next to each other is because they're opposites. Just like right here, the square and the square root function are next to each other because they're opposites. The log and the 10 to the x are opposites. The natural log and the e are opposites. So if we take the natural log of both sides, then since the natural log and the e are opposites, they cancel each other out. And by opposite, the actual word in math is inverses. These are inverses of each other, but in English we would just say opposites. Okay, since the natural log and the e canceled, that means that this side is just 2x. And all I need to do next is divide by 2 and divide by 2. So these are going to cancel. And if on the homework they ask for an exact answer, you just type that in. If they ask for a decimal, then... So we're using the ln right here. So just find ln of 4, and then that's divided by 2. And so it is a 0.693. And then for number 14, how about an 8, and then 7 is to the x, and it equals 164. So this problem is similar to the last one, except instead of an e, it's got a 7. So the work is going to be very similar. The first thing, though, I need to do is eliminate this 8. So I need to divide both sides by 8. And I'm sure that some people can just do that in their head, but I'm going to use a calculator since I paid for it. It equals a 20.5 on the right side. So then we have 7 to the x equals a 20.5. And just like on the last one, I'm going to take natural log of both sides. And you might be saying, wait a second, that's not the opposite of the 7 power. That's okay, because these are not going to cancel each other out, but my calculator can figure out natural log of 7, and it can figure out natural log of 20.5, so no problem. The next thing to do is, when you have a logarithm, this exponent, you could bring it in front and multiply. So when I do that, the left side is saying x times the natural log of 7 equals the natural log of 20.5. And so in order to solve for x, all I need to do is divide by the natural log of 7 on both sides. These are going to cancel, and then I have what x equals. And this, I definitely need a calculator for. So how much is the natural log of 20.5, and then that should be in parentheses, divided by the natural log of 7, that should be in parentheses, and it's a 1.552. Now with everything else, I've been so sure of my answer, I have not checked it, but I'm now going to check this answer. So if you go back to the original problem with the 8 and the 7 raised to the x equals a 164, I'm going to tell the calculator, check and make sure that this answer works. So first I'm going to tell the calculator, store this answer as x. So right here is the store. So store that answer as x. And now I'm going to type this in, 8 parentheses 7 raised to the x. And since I stored my answer as x, it's plugging my answer in right there. And if I did it right, it's going to equal this 164. So could I get a little drum roll? Yes, it worked. So this answer is correct. All right, so if you haven't taken a break, you might want to take a break, put it on pause and come back, because now for the applications or the word problems. And these are actually fun. I like these. So next is going to be about money. Well, that's part of the reason I like this, because it's about money. So if you put money in a bank and assume that you get a decent interest rate from your bank, then the money will grow and grow and grow, which is called compound interest. So at the end of 1 month, they will give you your interest. For me, that's like around 3 cents each month. I know, don't be jealous, 3 cents per month. And then if I leave that money there, then the 3 cents is going to get interest. And the next month, it's going to get more interest. And so it grows it grows exponentially, which is called compound interest. And the formula goes like this. The amount of money you're going to have in the bank depends on the principal, which is the beginning amount. So if you put $1,000, this is $1,000 plus, 1 plus, and then take the interest rate, so maybe something like 4%. And then the n is how many times per year that they pay the interest. And then it's raised to the n times t, and then t will be in years. So the p is called the principal, and then that's the beginning amount of money you put in the bank. So the r is the interest rate, and if it's given as a percent, which it usually is, then you do need to put it in decimal form. So if it said something like 4.1% interest, then move the decimal to the left by 2, and then we would be using the decimal 0.041. So move the decimal 2 places, then there'd be a 0 right there. And then the n is the number of times interest is paid. So for example, if it said it's compounded monthly, so at the end of every month, the bank says, okay, here's your 3 cents. All right, so that means that n would be 12 times per year, once a month. And then the t will be in years. Then, you know what, I'm going to go ahead and on this page do the other formula. So this is when, for example, the interest is paid monthly. But it could be that you go to the bank and it's not the end of the month. Maybe it's the 11th of March or something like that. And then they would have to figure out, well, how much money do we owe this person, even though it's not the end of the month? So that's called continuously compounded interest. Continuously compounded. So in other words, they're always giving you your interest, although it's going to be some tiny, tiny, tiny amount of money, but, or at least for me, it's going to be a tiny, tiny amount of money, but you could go to the bank at 3 a.m. and then they would say, okay, you're taking your money out. Here's how much you've got for interest so far. And I called this one the PERT formula. And so basically it's going to start with the A and the P, but then this part in here becomes the E function. So it's going to be A equals P and then times E to the RT. And this one is also used for biological type things where, for example, if you, let's say you take a glass of milk and you leave it on the counter for several days or weeks, well, there's going to be some bacteria, and then the bacteria is going to start growing faster and faster and faster, and the bacteria does not wait until the end of the month to suddenly have all the new bacteria babies born. So the bacteria, they're continuously growing. So that's when we use this formula. So it can be used in money situations, but it's also used in biology type situations with populations. Okay, then a couple of examples with that. And which number am I on? Number 15. So suppose that you invest $1,000 I'm going to go with the 4.1%. At 4.1%, and then for 9 years. I don't know why 9, but just let's say it's going to be 9 years. And so part A, how much money is there if it's compounded monthly? So the amount of money that you invest is the principal, that's P. This needs to be changed to the decimal form, so that's going to be the 0.041. This is how many years, so that means T equals 9. And then monthly, since there's 12 months in a year, that means N equals 12. So just use this compound interest formula and plug in all the numbers. So it's going to be the amount equals, start with the principal, 1,000, and then it goes 1 plus the rate, which is 0.041, divided, and then it's divided by the N, so the N goes here and also here. And then the last thing is the time, 9 years. And this would be a good time to use a calculator. So how much is, if it's $1,000 and then 1 plus the 0.041 gets divided by 12, and then put parentheses and raise it, and make sure that both of these numbers are in the exponent, 12 times 9. So then after 9 years, you would have $1,445, and since money we round to 2 decimals, that would be 38 cents. And then what if we do the same story, but it was compounded continuously? So that is going to be the PERT formula. So basically just use this formula. This is going to be the 1,000. This will be the 0.041, and this is going to be the 9 years. So it's going to be A equals $1,000 growing continuously at 4.1%, but put that in decimal form, and then the 9. And this should produce more money. Not a lot. It's not like it's going to be $5,000 or something, but it is going to be slightly more. So if you take the 1,000 and then put second E raised to the 0.041 times 9, and look at that, it's an extra dollar. So the amount equals, or almost an extra dollar, $1,446, and when you round that, it's going to be 29 cents. All right, then one other type of question. So this is example number 16. Suppose that you have a function like this. And at first you may think, well, this is something completely different. But basically when you have exponential growth, it goes like this and just keeps growing forever. And if this was your money, I sure hope that it would keep growing forever. But if this was a population, so for example, let's say you go to a national park where there's bears, and let's say that everything's been really good and the bears have been growing exponentially, not the bears themselves, I mean the population. So like the moms have babies, then the babies grow up, they have babies, so there's more and more. So it can grow exponentially. But if the park only has a certain amount of resources, and by that I mean natural resources like berries that they could eat or salmon or whatever. So if there's only a fixed amount of resources, then the population can grow rapidly, but eventually it's going to level off. And then this is called a logistics growth curve, used in business and biology a lot. Logistics growth curve, which just means it can grow rapidly for a while, but eventually it's going to level off. And then this is an example of a logistics growth curve. And let's see what it looks like. So graph this. Go to y equals, and then 300 divided by, and then put parentheses 2 plus the e to the negative x. And first of all, go to Zoom Standard, and it should look something like this. And I'm really only concerned with the right side, and I can't even see the right side right now. And it's probably because of this 300. So if you trace and you follow it out to the right, then you could see this y value. This is like 150. Well, right now it's 149. And it seems to be up in the 149 area. So for the x values, I could go from 0 to 10. And then the y values, I need to be up by approximately 149. So let me do 160. That should be good enough to see it. And hopefully it looks something like this. Yes, it does. And if I trace and I put 0, then it's actually starting at 100. And if you continue it out, hopefully you can see that, then this is 140, 145, 147, 148, and it seems to be leveling off at, seems to be around 150, which then makes sense to me because that right there, 300 divided by 2 is 150. So this is, again, let me put in when x equals 0. Oh, what happened? Oh, the window got moved over. Okay, so I wanted to know this point right here. So if you trace and you put in a 0, then it's starting at 100. And I'm assuming that it's something like this is over time. So I don't need negative time. I just need positive. So I just need the right side of the graph. And that was starting at 100. So it was starting at 100 and then basically leveling off at 150. So it's basically going like this. Okay, then for the last part, when is n equal to 125? So in other words, somewhere in here is the 125, and if you go across, there will be a time when it equals 125. So then the variable is x. What does x equal right there? So if you substitute and put n equals the 125, and then we need to solve for x. So in order to solve for x, this part right here needs to be in the numerator. So what I'm going to do is multiply both sides by the 2 plus e to the negative x. 2 plus e to the negative x. These are going to cancel. And I'm just going to leave this in parentheses. 2 plus e to the negative x times a 125 equals the 300. And next I'm going to divide both sides by 125. So eventually I'm going to get to this x, but I need to get rid of these things on the outside first. So divide by 125, divide by 125. Once these cancel, then on this side I don't need parentheses anymore. 2 plus e to the negative x equals, and then I'm just going to leave this because eventually I'm going to type it in the calculator, so I might as well just leave this alone and not even reduce it or anything, just leave it like that. And then subtract 2 from both sides. So then I have e to the negative x equals 300 divided by 125, and then subtract a 2. And just 2 more steps. One is take natural log of both sides to eliminate the e. So these are going to cancel. And then how much is this? So on the left side, the 2 would cancel, leaving just negative x equals the natural log of this, which I'm about to type in the calculator. And then for the last step, we'll just need to multiply by a negative to find out what x equals. So if I do this part, the natural log of a 300 divided by 125, and then minus a 2, and all of that's in parentheses. So that's what it would be when I have the negative on this side. When you multiply this by a negative, it turns out that it's going to be a 0.916. So that's the end of today's lesson, but if you want to stick around just for a few minutes, I want to show you something else you can do with the calculator and money. And this is very, very helpful in real life. So if you go right here to apps, then finance, and the time value money solver. So what this is basically how loans are calculated. So let's say that you are going to buy a car. So the present value of the car, let's say you're going to go fancy and you're going to pay $50,000, or you're going to borrow $50,000 for a nice fancy car. And these days the interest rates are pretty high, but let's say you've got excellent credit, so you get a 5% interest rate. And then you need to figure out, all right, how many months am I going to pay? So in other words, this n on the calculator means in total how many months. So let's say you pay for 5 years. So 5 times 12 months, that means you're going to pay for 60 months. You're going to pay 5% interest. You're borrowing $50,000. The FV means in the future, you're going to owe 0. And then how many payments per year? So let's say you pay just once a month. So this is 12. And then this means compounded monthly. And then after you have all that set up, go to the payment. And then to figure out what your payment would be, go over here and put the solve. So in green, this is solve. So then I need to go to alpha solve. And then it says that your payment is going to be $943.56. So if you ever go to a car dealership and you do this, and then they tell you your payment is going to be $975, you go, wait a second, no, because my calculator says it's going to be $943. And the other cool thing is you can say, you know what if I'm feeling really rich and I can make a payment of $1,100 a month? Who knows where you're getting all this money, but anyway, let's say you could pay $1,100 a month. Then you could go up here and ask it to solve for the n and say, well, how long is it going to take me to pay it off? So that basically saves you almost 10 months by paying $1,100 a month. So anyway, that's a really cool real life application for the calculator. All right, see you next time.